Hi guys, welcome to this new session of Wants for CFA Level 2. Today we'll be starting with a new reading which is time series. So time series is the third and final reading within the regression content of CFA Level 2 Wants. You still have three more readings left after time series, but those are mostly relating to machine learning, big data, and that stuff. They have been introduced newly in this syllabus, so they are a little bit more theoretical than they are practical in terms of calculations. So time series is sort of the conclusive reading for our regression content. So time series is directly linked with the content we've covered so far in linear and multiple regression. So let's jump in right away. The first thing that we need to understand is what exactly is time series. So the first section is a basic introduction. Now, time series is basically just a specific type of regression analysis in and of itself. Where we exactly use it is when our data set is spread across multiple time periods. So if I go to our example that we took in the very first topic, Sensex and Reliance, both of those share prices and the Sensex values, they are sort of a data collected at different points in time. There were daily prices collected for the last quarter of 2019, all the way from 1st October to 31st December. So Q3 for India, Q4 for any students in US. If I look at any of that data set individually, so let's say I'm looking individually at the prices of at the value of Sensex, that data set is representing different time periods as well. So that data set not only has values, but it also has an element of time change happening gradually. Whenever I have that kind of a data set, I can always refer to time series to explain that particular data a little bit better. So the most common form of equation we have for time series is so this is our most common notation of a time series equation. It is y is equal to b0 plus b1 t plus error term. Now, if you look carefully, in comparison to the linear regression equation, only one thing has changed. Our independent variable in case of linear regression used to be x. We had a different data set that we used as an independent data set to predict the values of the dependent variable. In this case, time is my independent variable. Now what is happening is we'll use these denotations. So what I'm trying to do now is I'm trying to see if I can predict the value of y simply by using the passage of time as my independent variable. So normally this is done in cases where I'm observing a pattern emerging in the price movement over time. So let's say a particular stock over the last year, it has gradually increased every day by some percentage, or let's say it has gradually increased by 2 or 3% every month. I want to know if there is, at the very beginning, is passage of time in and of itself a relevant factor? Like, can I actually say that this stock is good enough to the point where just passage of time by itself is a factor enough to justify or to explain that increase in price? So normally if we had a linear regression and we had x in this place, our equation would simply say how much movement of y is being explained by x. In case of a time series, we are simply saying how much movement of y can be explained by a simple fact of passage of time. So all I'm doing here is I'm trying to explain the movement in my variable as a result of passage of time. Because at times I might want to know If the increase or decrease in prices of my particular stock or anything else you take as a dependent variable, does this have a justification that is purely dependent on time? If it is not exactly dependent on time, then we start looking at other factors, like we looked at Sensex in our case. So, looking at my dependent variable and seeing how much of movement over here is explained by the simple passage of time. This is my time series. This is used to judge certain trends that are emerging within my data set. And when I say trends, I'm always talking about trends with respect to time. So, if something is constantly increasing as the time passes by, this would help me identify if the passage of time is a relevant factor or not. Now, so far I've been saying whether passage of time is relevant or not. If you go back to linear regression, we had x in place of t, and to decide whether that was relevant or not, we used to check whether b1 was statistically significant or not. If b1 ended up being statistically significant, it inadvertently meant that yes, x as an independent variable is relevant for me. I can use x to explain the variation in y. We are going to do the exact same thing. So time series, the only thing that has changed is my independent variable is now a simple passage of time factor. Once again, to decide whether this passage of time is actually relevant for my dependent variable or not, the process is same. I'll run an equation using the data of y and a simple data for t. So t would basically be, if I have 60 days of data, I would simply label them with days. So first day would be labeled 1, second would be 2, third would be 3, so on. I'll have numbers till 60. Once I have this equation, I'll have a value for b1. Again, the equation is something you'll get from the Excel itself. You don't have to know how to get the equation. Once we have the value of b1, the simple process, just like we had in linear regression, we use t-test, confidence interval, or p-value. You can use either of these three. The results would be same to decide whether this b1 is statistically significant or not. Same process as linear regression. If this b1 ends up being statistically significant, it means that passage of time in and of itself is a very good explanation of the movement in my prices of y. And if this b1 ends up being statistically insignificant, like it's not very relevant, then we'll simply conclude that passage of time by itself is not a very relevant factor in explaining the movement of y. So time series is simply replacing my independent variable with passage of time. That's it. I'm trying to analyze patterns that emerge, the trends that emerge simply as a result of time. So let's look at some graphs. So this particular equation, this is a case of linear regression itself. So if I were to draw a graph, I would have y on the y-axis, and on the x-axis we'll have time. The equation would be something like this. Assuming b1 is positive, if b1 is negative, it would be downward sloping. Now, if you remember, this is the exact same graph we had for linear regression as well. The only thing that has changed is on my x-axis, I used to have my independent variable, but in case of time series, I have time. So now I'm looking at y as the time passes by. So this is my linear trend. Now in real world, it is not always going to be true that my trend is always linear. We also have a case where my trend is something like this. Now, we often observe something like this in case of new companies or newly listed companies for that matter. When a company just starts its business, it's not going to have too much variation in its valuation. But As it starts to stabilize its operations, the valuation really starts to increase rapidly. So we have something like this. This is a case of an exponential growth. Now, in case of exponential growth, if you remember all the way back to linear regression, because at the end of the day, time series is still a linear regression at its very core. The assumption was the relation between dependent and independent variable has to be linear. In this case, the relation is not necessarily linear. So, what I want is there should be a line that I could use that fits my data set and that captures most of its variations as well. This particular case is known as a log linear trend. So let's look at this log linear trend in the form of an equation. So over here, this line is denoting the same thing we had, b0 plus b1 p plus error. Whenever we have an exponential relation, it is quoted as something like this. What I am doing with the straight line, so this is represented by this dotted line. I'll just make the straight line solid. What I'm doing with the straight line is I am changing the axis to log natural of y. So initially my axis was y and my relation was exponential in nature. What I am doing now is I am changing the axis such that now my relation becomes linear so that I can continue to use my linear regression. So in order to convert this, we simply have log natural of y is equal to b0 plus b1. Now this equation is representing a linear relation. All I've done is instead of having y as my axis, I've changed my axis to log natural of y. So in case of exponential relations, we can often convert them into linear so that we can still continue to use linear regression for the analysis purpose. The relation is still going to exist in an exponential form, but I can often use the results from linear regression to interpret that actual trend emerging in the market. So we have linear trends and we have log linear trends. Now let's look at an example as to how y might be predicted in case of log linear trends, just to clarify some doubts that you guys might be having. So let's look at that. So I've just written some values here for the example. You have the value of intercept given to you, b0. You also have value of slope coefficient given, and the time factor is given as 100. So we are checking at the 100th point in time. And this is the equation. Now, the moment you see an equation like this, the first thing you have to understand is this is a log linear trend. So this is not a linear trend outright by itself. This is a trend converted into a linear trend. This is originally an exponential equation. So this represents that we are dealing with a log linear trend model. Once we know this, we simply try to figure out the actual form of this equation. Now, if I want to know what the actual relation was, I can simply reverse it to how the exponential notation would be. So I can reverse it to say e to the power b0 plus b1 t. Now, if you remember just, in the previous section, what we did is this was the actual relation and we converted it to a linear format so that we could use regression to still perform our analysis. But now what I'm doing is, because I have to get the value of y 100, so I basically need this value. If I need this value, I'm reversing the process and now having an exponential equation back with me. So y100 is equal to e to the power of 20 plus 0.02 into 100. So I have y to the y 100 is equal to e to the power of 22. This you can solve directly in the calculator by using the function ex. So simply put the value 22 and then press this function, you will get the value of y100. This value would come out somewhere close to 3.584 billion. So how you calculate? A very brief example to just get you guys familiar with the calculation part. So that's the first part. We've discussed how what time series is, how they work, two separate kinds of trends that we often analyze using time series. So we have linear and we have log linear. Let's move on to the next topic. The next topic that we have is autoregressive models or AR models. Now, what exactly is an AR model? Well, when the independent variable is a lagged version of dependent variable, then the sort of regression or the time series that we have is known as an autoregressive model. So just to clarify that, think of it as x t x t minus 1 plus error. So what I have here is I'm trying to predict the value of x right now using the value of x one time period before as my dependent variable. So I'm trying to predict stock price of any share today on the basis of what the share price was yesterday. So that is my t minus 1. Now, the definition says it is a lagged version. So this lag can be of one time period, it could be of any time period. So if there is a general notation, it would be t minus k. K could be anything. I could have t minus 1, t minus 2, t minus 10, whatever you like. So all of those are acceptable. Now, one more thing to understand here is in the very basic form, it is always a sort of a linear equation. But as we cover this topic further within autoregressive models, we'll find out something known about seasonality. And in that case, we often modify it to become a multiple regression. So just keep an open mind. It's not always linear. It could be converted into a multiple as well. But the key thing is it is a lagged version of my dependent variable, which means X is used both as independent and dependent variable. So I only need one data set in this particular case. I have one data set. On the basis of past values, I'm trying to predict the future value. That is my autoregressive model. Now, autoregressive model has one very key factor. Any regression done on AR model. So AR model regression is usable if the AR model is covariance stationary. Now, this is simply saying that, I have this equation, I have run a regression on it, I have received values of B0, B1, B2, or normal analysis, t-test, confidence interval, p-value, f-stat, r-square, all of those. This statement is simply saying all of those are usable only and only if this AR model is in fact covariance stationary. Now, what exactly does this mean? What is covariance stationary? Well, covariance stationary is a sort of classification we give to an AR model if it satisfies three conditions. So if an AR model satisfies three conditions, we classify that model or we approve that model as being covariance stationary. So in reality, what is happening is if my model complies with these three conditions that I'm about to list, if these three conditions are satisfied within my model, I can use regression to analyze this model. If any of these three conditions are not met, I cannot use my standard regression to analyze this, because in that case, regression would work. I mean, software would still give you values, but those are not very reliable values. So if I want my regression to not only be usable, to also be reliable, these three conditions which I am about to specify, these have to be met. So just remember, these three conditions together are given this term covariance stationary. It's not something entirely out of the blue or anything fancy or such. It's just a name given to a combination of these three conditions. So in reality, if these three conditions are met, you can use regression on the AR model. If these three are not met, you should ideally not be using the regression model in an AR, because the outputs given by the regression model are no longer going to be statistically relevant, or rather, the precise way of saying it is they won't be statistically reliable. So let's look at these three conditions. So first is constant and finite expected value. For now, just write it as mean reversion. We'll discuss what this mean reversion is in a later topic. It's not very relevant for this discussion, but we'll cover it within time series itself. So just write mean reversion, we'll discuss it later on. Constant and finite variance. And constant and finite covariance between a given lag. So we've had a condition like this for linear regression where we want the variance to be constant. So that same condition is here. So this is nothing new. This is exactly same as the assumption we had in case of both linear and multiple regression. The new part is this, the last one. It is saying on any given lag. So once I have a fixed value of k, let's say I take k to be 4. I'm analyzing xt in comparison to xt minus 4. Once I have a lag fixed, the covariance between xt and xt minus 4 should be constant and finite. Covariance, again, if you understand correlation from level 1, covariance is the same thing. It is just a judgment of how related the two sets are. Now, I have one data series, but I'm converting it into two by taking xt in one side and xt minus 4 in the other side. So I'm simply, taking the fourth value for xt minus 4. That's it. So the covariance between those two, between any given lag, has to be constant and finite. So now that we have these three conditions done, let's look at an example as to how we'll predict xt if values are given. Again, a very basic mathematical calculation. Let's look at that. So here is a small example to let you guys a little bit more familiar with the AR model. So a question could give you, this kind of an information. They give you a base equation and they give you values of t minus 1, b1 and b0. Once you have all of this, the question is saying find out what the value is of xt plus 2. Now, if you look carefully, xt plus 2 is not outright there in the equation. So it's not as simple a case as just plugging in the values and getting the answer. It is just a case of you having to use this equation multiple times. So it is known as chain rule of forecasting. Now, if you look carefully, xt plus 2 is not, outright easy to find from this equation. Like we can't simply plug in all the values and get xt plus 2 directly. What we'll have to do is we'll have to use this equation multiple times. Using the equation, AR equation multiple times to find out the target value is known as chain rule of forecasting. So what we'll do is we'll first find out the value of xt. Xt would be b0 plus b1 into xt minus 1. This comes out as 70. Once we have the value of xt, I can give another iteration to this equation, which is x t plus 1 is equal to b0 plus b1 xt. All I've done is the equation said there has to be a lag of 1. A lag of 1 means if I have dependent variable as xt, my independent was supposed to have a lag of 1, it would be t minus 1. I've just used this same principle to write this equation in another form where now I'm saying my dependent variable is xt plus 1 and my independent variable is xt. If you notice carefully, both of these still have a time lag of 1. So my equation is still going to hold true. The equation gives the characteristic of my entire data set with a specified time lag, which was 1 in our case. So now that we have this, we can calculate xt plus 1 using the value of xt that we just found out. So 50 plus twice of 70. Once we solve for this, we get 190. And then we can rewrite this equation into third iteration. T plus 2 is b0 plus b1 x t plus 1. This would result in 430, which is your final answer. So basically what we're doing, so far, whenever we had to predict the dependent variable, we were simply plugging in all the other values and figuring out what the value of y is. We've done that a few times so far in linear and multiple regression. The only thing that is changing here is we have to do this stepwise multiple times if we have to forecast a value multiple time periods ahead. This entire process is known as chain rule of forecasting. So just a new name, nothing complicated here, nothing as such technical, a very basic concept. All I'm doing is I'm using the logic that once I have an AR model, I'm not concerned with the actual notation of the equation. I'm concerned with the lag that the equation is denoting. So if this is my AR model, this AR model is going to hold true for all the iterations that have a time lag of 1. So all I'm doing is I'm just using that characteristic of an AR model that once a time lag is specified, for that time lag across the entire data set, my equation would hold true. I'm using that characteristic to predict the value of my dependent variable multiple time periods in the future. So I hope that clarifies. Now, within this AR model, we have one major complication, which is, well, we've covered it on multiple regression. It is serial correlation. Another name for serial correlation is autocorrelation. So if you see the word autocorrelation or serial correlation used interchangeably, that is just because both of them mean the same. You can also use both of them interchangeably. So let's look at that. The next sort of major topic that we have to cover is serial correlation in AR model. Now we've just looked at a basic AR model so far. AR model is basically when I use a lagged version of the dependent variable as an independent variable. So first of all, to understand the AR model itself, let's take a look at a practical example. So if you remember from the linear and multiple regression, we've been using Excel file to look at a practical example. So what we'll do now is, let's use the Reliance prices that we had from linear regression from 1st October all the way till 31st December. Let's look at the Excel file. Now, if you look within the Excel file, what you'll observe is I just have data for Reliance for all the 59 days with me. So I just have one single series. Now I will use this singular series to create another series which would be a lagged version. So basically, Reliance price on day 2 should be predicted by the Reliance price on day 1. So basically what I'm doing is I'm trying to predict next day's Reliance price using the first day's stock price. So from one series, I'll basically create two. All I'll do is I'll change the lag. So what would happen now is initially we had 59 observations. Now we'll only have 58 observations. Now, once we have this, the process of running regression is same. You just select the regression from data analysis tab. And once you're done with that, you get the exact sort of same table. You get ANOVA table, regression table, R square, everything is calculated for you. And we even have residuals. Now, if we move on to the discussion about serial correlation in the AR model, the most important thing is to remember what serial correlation was. Now, if you go back to multiple regression, we've discussed serial correlation is when error terms of two different observations, two different residual terms have a correlation. So our assumption was that different error terms should not be correlated. The correlation between error terms I and j should be 0. Now, in case of an AR model, all my error terms are also representing time. That's why in AR model, we represent error as error t, because error is for first day, then second day, third day. So we have 58 error terms with us. Now, in order to understand whether there is a serial correlation or not, whether error terms are correlated with each other or not, we need to run a autocorrelation or just a correlation on error terms with different time lags. So just like we had xt and xt minus 1. So in the AR model, we had xt and xt minus 1. Similarly, now for the purpose of serial correlation, I'll use error t and t minus 1. Now, how exactly do we get both of these series? Let's jump back to the Excel file. Now, if you observe, we have all the values of residuals provided to us as a result of the regression itself. Just like we created a second series for Reliance using stock prices, we can create a second series for error term with a time lag. So that now we have error terms t and error terms t minus 1. Similarly, we can go ahead and create multiple time series error terms t minus 2, t minus 3, t minus 4. We can do this as many times as we want. Now, all we have to do once we have these multiple error series is simply select any two series out of these. So let's say I select error t and t minus 1. And then we simply calculate correlation between these two series. So now we're not running regression again. I am simply calculating correlation because my serial correlation was more concerned with correlation part rather than the regression part. So all we'll do once we have these multiple error series is we run a correlation on both of this. Now, in order to understand what exactly this correlation implies, how do we do the analysis? Let's look at an example where some of these correlations are already calculated. So let's move to the example. Now here I have an example, and this is sort of the table that you should be expecting in the exam. You won't get the entire Excel kind of format where you have 50 or 100 different error values, you'll get something like this. Now, let's quickly relate with what we've understood from the Excel with what this example is. Now, mind you, the values in this example, these are separate. These are not the values from the Excel itself. So this is a separate example. The Excel part was just to explain you how all of this might be calculated. So in this table, when we say lag 1, it means error t and error t minus 1. So basically the lag between my error terms is that of one time period. When I say lag 2, it is error t and error t minus 2. Similarly, this is between t and t minus 3. This is t and t minus 4. Now, just like we had in the Excel file, once we created the different error terms, this error series, we simply calculated correlation between the two. That correlation is my autocorrelation. So autocorrelation is simply correlation of error t and error t minus k, where k is basically the lag. So in case of this, 0.09 is the correlation between error of series t and error of series t minus 2. So basically, just to give you an understanding what the values in this table is, because this is exactly the kind of table you'll get in your exam. So I have different error lags and I have corresponding correlation already calculated for you guys. Then we have something known as t-stat. Now, if you remember from linear regression, we had two calculations. One was confidence interval, the other was t-stat. This is t-stat. So t-stat, if I go to the very basic form, b1 minus the b1 that we had assumed in the hypothesis, this was always equal to 0, divided by standard error of b1. So this is what we had in linear regression. Here also, once I have the correlations, if you look logically, I am trying to prove whether serial correlation exists or not. And just to clarify, I know a lot of you might be confused there. Autocorrelation is just another name for serial correlation. So don't think these two are different concepts. No, they are the same. Serial correlation, autocorrelation, they are two terms that are used interchangeably. They mean the same thing. So when we look at t-stat from linear regression, this is the sort of calculation we had. And normally we were trying to prove that b1 is different from 0. In this particular case, I want to check if there is serial correlation or not. So if I want to check, or rather if I want to prove that yes, there is serial correlation, it means that some of these autocorrelation values that I have, they have to be statistically significantly different from 0. So I'll repeat that part again. Just like in linear regression, we were testing whether b1 was statistically significant or not, it was different from 0 or not. Here also, if I can prove that one of this correlation value is significantly different from 0, it is statistically significant by itself, I would automatically prove that yes, error terms are correlated with their own lagged versions and there is autocorrelation or serial correlation in my AR model. So again, I'm trying to prove the autocorrelation is statistically significantly different from 0. So just like over here we had b1 as 0, in case of t-stat, we have, or this particular case of t-stat, we have correlation. So the autocorrelation part, I'm just going to write it as correlation A minus 0 divided by standard error. Now standard error here is denoted as 1 divided by root of t. This part you'll have to cram for the exam. I don't have any sort of detail that I can get into that would not confuse you. So I don't think looking at this part in much more detail is worth the time, because it would only end up confusing you even more, particularly when we are towards the end of the regression. So I don't want to start a whole new discussion which is not relevant for the syllabus as well. So this part you'll have to just cram it. So basically standard error in case of autocorrelation is denoted as 1 divided by root of t, where t is number of observations. So if my number of observations is, let's say, 25, this would be 1 divided by root of 25. So that's my standard error. Now, the reason why I'm giving you this is because in exam, normally this entire table would be given to you. You won't have to calculate t-stat also. But there is a case where instead of given t-stat, you will be given value of capital T. Now you can use this correlation value. Basically, this is my correlation, autocorrelation. So I can use this value and divide it by 1 divided by root of t to get my t-stat. That's how all of these values have been calculated. So I hope all of that makes sense. Once that part is done, once we have all the t-stat values for different lags, the next step is exactly same as linear regression. In linear regression, if you remember, in the regression table, we got the t-stat value. After that, we were simply checking whether that t-stat is within the critical range from the t distribution, or is it outside the critical range from t distribution. Now, in order to check the critical range of t distribution, we need degrees of freedom and we need level of significance. Let's look at those two things. Now, in our case, in serial correlation, degrees of freedom is always going to be t minus 2. So in my question or this example, I've assumed t to be 40. So there are 40 observations. Degrees of freedom becomes t minus 2, 38. And let's take level of significance as 5%. Now you won't find the exact 38 value for degrees of freedom in the t distribution that is often provided to you. So just for the sake of simplicity, we'll take the most approximate value, which would be somewhere around plus minus 2. So the critical values from the t distribution is plus minus 2, which simply means if my t-stat is within the range of plus minus 2, I'll simply consider that yes, my autocorrelation is more or less close to 0. It's not statistically significant. It's insignificant. I can ignore it. But if my t-stat ends up falling beyond this range of plus minus 2, that would raise a red flag that now my autocorrelation is statistically significant. So all we have to do now is use this range to check if any of the 4 t-stat values are proving that my correlation is statistically significant. So if you look carefully, it's the 4th t-stat value which is beyond the range of plus minus 2, which means this correlation 0.45, this is statistically significant. This is different from 0, which means there is serial correlation between error terms t and t minus 4. So when I take a lag of 4, I have a serial correlation. I don't have a serial correlation problem with every single lag, but I have it when I take a lag of 4 in my particular distribution. So I hope that part is clear. That's the first part of this entire discussion. The second part is how exactly, or now that I know there is serial correlation, how do I correct it? Now, if you remember in multiple regression, we used Durbin-Watson statistic. Well, here we won't use that. That is not really something we can replicate one-to-one in this particular case. So now whenever we are dealing with an AR model, the serial correlation is something that is not necessarily wrong for me. Rather, it is a way for me to improve my AR model. How so? Let's look at that. Now, before I explain anything, I just want you guys to take one simple assumption or clarification. Let's assume the data that I have for whatever the distribution was that created this. So in this example, whatever the data I had, let's say that was quarterly data. Now, if we have quarterly data and we've done all of this analysis, we know that at the 4th lag, we have a serial correlation. In case of AR model, the existence of serial correlation implies something known as seasonality. So serial correlation in AR model is not something that makes our regression outright unreliable. Rather, it's something that gives us an opportunity to improve on our AR model. So whenever we have any sort of serial correlation present in AR model, it indicates seasonality. Now, if my data is quarterly and on the fourth lag, I'm getting a significant correlation. It simply implies that every fourth quarter, so after first quarter, fifth quarter, then ninth quarter, all of these are going to be linked somehow. That is why this correlation exists. So basically what I'm saying is, if I have Q2 in 2019, the Q2 in 2020, that is basically the fourth lag, that would be linked with each other. They would be correlated. So Q2 across multiple time periods, multiple years would be correlated with each other. Similarly, Q3 would be correlated with Q3 values of all the years. Q4 would be related with Q4 values. So whenever I have a lag of 4 basically means same quarter next year. Whenever I have a lag of 4, I have significant correlation, which means my error terms are not random. They have some explanation that they can derive from the error term 4 time periods before the existing time period, which indicates seasonality. So, how exactly do we deal once we've identified there is seasonality? How do we deal with it? Well, it's a very simple logical step that we take. Now, if I just say that the initial equation was this, so xt is equal to b0 plus b1 x t minus 1 plus error. So this was my initial equation. If I am to introduce seasonality over there, so I've recognized from this example that yes, there is a seasonal element at the lag of 4. So once I've identified seasonality from this analysis of serial correlation, I will try to modify this initial equation. What best way do I have to modify it is I will add another independent variable, which would also be a lagged version of dependent variable. Only this time, the lag would represent the seasonal element. So I know that seasonality is existing at a lag of 4. So I'll have xt is equal to b0 plus b1x t minus 1. So till this part, it's the same as what we had. We'll add another independent variable x t minus 4 plus error. So now what I'm saying is any quarterly results depend on two factors. The quarterly results for the immediately previous quarter and the same quarter last year. So what I've done now is I've introduced another independent term, which is also a lagged version of the dependent variable, but this time it is trying to incorporate seasonality within my regression. So this is how you incorporate for seasonality. So I'll just quickly recap all of this part. The reason why we need to study serial correlation in AR model is because it implies seasonality. Now the analysis is simple. You take multiple lags and you calculate correlation. If any of that correlation is statistically significant as per the t-stat, then it implies that yes, a particular seasonality might exist. How do we correct for that? We simply introduce an independent variable with the same lag as the one that had a significant correlation. Now, in an ideal world, once I have done this, I'll run the regression again, now using two sets of independent lagged variables. This time, when I get the regression and I do the same analysis again, none of the correlations should be significant. So basically what this should do is, once I run the autocorrelation part again on this particular regression, this 0.45 should reduce to something statistically insignificant. Basically, all my t-stand values would be within the range plus minus 2. So that completes our discussion about serial correlation in AR models and the seasonality. One last thing you need to note. Now, in our case, we had quarterly data, so it is only statistically relevant for us to have lag of 4. I could easily go with a lag of 5, 6, 7, 8, all of those, but they won't logically be relevant. So if I have quarterly data, my common sense says anything that is repeating, anything that is seasonal, at max it can repeat at an interval of 4 quarters. Similarly, if I have monthly data, I would only analyze till lag of 12, because any seasonality that exists beyond the lag of 12 is not something that my common sense would allow me to think about. So we only take lags till the point where seasonality can actually exist. So statistically, numerically, you can take this lag all the way to 10, even for quarterly data. But thinking from a common sense point of view, a lag of 9, even if it comes out with some significant correlation, we would never be able to explain that as a seasonality. I cannot, there's no way for me to say that Q1 in 2018 is significantly relevant to explain the error term in Q3 2021, because there is no logical explanation there. So logically, whenever we are dealing with financial data, we normally take the lag in respect of the data. So if it is quarterly data, I have only 4 lags that are relevant for me. If I had monthly data, I'll take 12 lags. That's it. So that was just a clarification I wanted to give you guys. That completes the discussion about serial correlation. So you don't have separate calculations or the second step of autocorrelation in seasonal corrected equations. This is the practical part. This is the correction part. Just know that why we introduced t minus 4, because, well, fourth lag was relevant. So that concludes the entire discussion about AR models, and that also concludes this first session in the time series reading. So we have one more session in time series, and that session would include some of the remaining topics of multiple regression as well, and we'll conclude this entire 6-part series of regression as a whole. So we started with linear, multiple. After next session, we'll conclude time series as well, and that would complete the entire regression part of your quant CFA level 2. So if you have any doubts, queries, feedback, you can always contact me. I leave my contact details in the description. I'll also leave the Excel file that we looked at for the time series. I'll link that also in the description. So as always, I hope you enjoyed it, had fun, found it informative. I'll see you in the next one. Goodbye.